8.1, Example 3, Modeling Exponential Growth. So the example here says, in the last 10 years, an initial population of 44 deer in a state park grew by about 8% per year. Well, an exponential growth model just takes the form A, the initial amount, or the initial population, times the quantity 1 plus r, the rate, okay, in decimal form, raised to the power of t, which is time in years. So this is going to be the formula that we are going to use. So A says, write a model giving the number of deer, after t years. So we're writing a generic model that is going to leave t as a variable so that we can plug in anything that we want. And then we're going to answer the question about how many deer were in the park after 5 years. Then we're going to graph the model and use the graph to estimate what year were there 60 deer. So the initial population is A, and in the example it says that the initial population of deer is 44. So we have 44 deer, so that's our A. Okay, so A is 44, and the percent increase is, well, it says 8% per year. Well, 8% in terms of a decimal is 0.08. So that means that the exponential growth model, A times the quantity 1 plus r to the t power. If I plug everything in, I'm just going to substitute in for A and r. So A is 44 times the quantity 1 plus 0.08 raised to the t power. Okay, remember, I'm keeping t generic because I'm writing the model for it. Okay, so 44 doesn't change, times the quantity 1 plus 0.08 is just 1.08 raised to the t power. Now, using this model, we can estimate the number of deer after 5 years by just substituting 5 in for t. Okay, so d equals 44 times the quantity 1.08 to the 5th power. Now, if we do that on the calculator, so just go ahead and get out your calculator and enter it in exactly how it looks on there. You can, if you're using a TI-84, you can use the parentheses and everything else, and it will do all of the hard work for you. And after 5 years, you'll see that we get 64.65, and since we don't want to have decimal points of deer because we don't have any deer missing legs or anything like that, we're just going to make it a nice round 65 deer. Okay. So now, when we graph it, we can see that if we plug in 0 for x, okay, so if we plug in 44 times 1.08 raised to the 0 power, well, that's our initial population because 1.08 to the 0 power is just 1. 44 times 1 is 44. So 0, 44, and then if we plug in 1, that would be 44 times 1.08 to the 1st power, which would just be 44 times 1.08. And if we do that really quickly on the calculator, we get 47.52, which would actually just be about 48. But for the purposes of the graph, we'll go ahead and put 47.5, just so that we can get a little bit closer, maybe, although on this graph, since the tick marks are going in increments of 15, it's going to be a little bit difficult. 0, 44 is going to be basically just touching that side of the line, and 1, 47.5 is going to be just above that side of the line. Okay, and then I already know 5, 65. So if I go to 5, 65, that's going to be about a third of the way up above the 60 mark, okay? So now if I try and curve this, it's going to look something like that, okay? It's a very gradual curve. But I can see at 60 years, or excuse me, at 60 deer, okay, 60 deer is right around here, which means that that was after 4 years. So the population of deer was 60 after about 4 years. Now, moving on to compound interest. If you have an initial principal deposited into an account that pays interest at an annual rate R expressed as a decimal, so that's important. So we're going to again be converting a percent to a decimal, compounded n times per year. So is it compounded monthly, 12 times per year, daily, 365 times per year, weekly, 52 times per year, okay, or it's just compounded once a year. Then we use the equation A after t years. So A is equal to P, the initial investment, times 1 plus R over the number of times it's compounded, raised to the number of times it's compounded, times the number of years that it's in there. Okay? So that's how we find compound interest. So from here on out, basically, it's just plug and chug. Okay? All you have to do is know what P is, know what R is, and know what N is, okay? And then you can solve for any length of time you want. So in example 4, and we're going to find the balance in an account. So our initial deposit is $1,400 in an account that pays 4% annual interest. Says find the balance after 1 year, so we're going to use t equals 1 for all of these. And then we're going to do it 3 different times, compounded with the different frequencies. So annually means that n equals 1, okay? Monthly means that n equals 12. And daily means that n equals 365. Okay, there's 365 days in a year, 12 months in a year, and 1 year in a year. Okay, so now I'm going to go ahead and write down all of our pertinent information over here on the side, okay, so that we have it available to us. So we have P is equal to $1,400. R, the rate, is equal to 0.04, 4%. And T is always going to be equal to 1 year. Okay? And then my N is going to vary for the different problems. So that's the only thing that I'm going to change. So now I'm going to scroll up a little bit, and we've got everything that we need right here for the different ones, and I will color code them. So we'll start with A in green. Our N is equal to 1, P is equal to 1,400, R is equal to 0.04, and T is equal to 1. So 1,400 times 1 plus R, which is 0.04, over N, which is 1, raised to the N, which is 1, times T, which is 1. So that would be 1 plus 0.04 divided by 1, so 1.04, raised to the 1 times 1, which is 1. So then 1,400 times 1.04 is equal to 1,456, which means that our balance after 1 year is $1,456 even. Okay. B, we're going to do the exact same thing, only we're going to use N equals 12, okay, because now we're talking about monthly. So that would be 1 plus 0.04 over 12, my new N, times 12 times 1. So that would be, first of all, we need to find an approximation for 0.04 divided by 12. which is 0.00333333, etc. So 1400 times 1.003333, etc., raised to the 12 times 1, which is 12. Okay, so if I plug that all in, 1400 times that 1.003333 raised to the 12th power, I get $1,457 and about 4 cents. It's actually 0.038, which gives me, rounds up to 0.04. So my total in the account is $1,457 and 4 cents. Okay, so it went up a little bit, compounding it every month instead of every year, but only by about $1.04. Okay, and then the last one, so we're now going to compound daily, so n equals 365. So I adjust everything, 1 plus 0.04 over 365 raised to 365 times 1. And again, I simplify, starting by 0.04 divided by 365, and it's a pretty outrageously small number. Okay, so it's like 0.000109589. I will round that a little bit, so 1400 times, when I add that to 1, I get 1.0001009, and I'll cut it off there and say 6, raised to the 365th power. Okay, so once I plug that in on the calculator, I get $1,457.13. So my account balance at the end of the year, $1,457.13.